Let's get started. So I've been watching the Piazza post. I'm not going to pull up the Piazza post again every lecture, but I've been watching the Piazza post. The things, for the most part, the same, except the classes in OOP and Python is by far the winner, far and away the winner. Today is still LO3 review, so I'm going to just confine myself to the LO3 topics, anything remotely related to LO3. That's what I'm looking at for today's lecture. Monday's lecture is going to be the quiz review. I'll go over the solutions to this week's quiz in Monday's lecture, at least one version of it. And Wednesday, possibly Wednesday and Friday next week, I'll do classes in Python. My intent is to go through homework 2, just go through as much of homework 2 in Python as we can. It might take 2 whole lectures to do that. Of course, barring any changes, if there's something new that's posted that gets a lot of traction, or something that's already posted gets a lot of traction on that post, and of course I'll do that too. Aside from classes in Python and graphs, which we already did, the third, fourth, and fifth most voted were all having to do with runtime analysis, so that's what I'm going to do today. There was going over all the n stuff, I think the thing was, which I assume is like O of n, O of log n, O of n log n, things like that, which I'm prepared to do today. Another one was more runtime analysis stuff that got quite a few votes. Mostly the same thing. I see those as the same. I don't know how to do anything different based on those. And one was binary search, which got a decent amount of traction. So I'm going to roll binary search in there. So while I'm doing runtime, I'm just going to throw binary search in there. It's part of the runtime analysis. So let's do that. So I'll do those 3 things, those 3 posts today. And the only one left that really got, of course, the most and tons of traction is classes in Python, which will be next Wednesday and Friday. As always with these demo lectures, where I'm just kind of going through things that I think will be interesting and according to the votes and everything, if there's something that you want to see, feel free to put it in the chat or raise your hand. I'm fine just guessing what you want and just going through whatever I have prepared. I can go on for 10 hours just doing this kind of stuff, much less 50 minutes. But I'd much rather go off of what you all want to see. So if you have something, any suggestions or anything, let me know what you want to see. What do you want to learn about? Otherwise, I'm just I only have, just like last time I had graphs, 1 word to go off of. I have a few more words, runtime analysis this time to go off of. But I'm just going to kind of do whatever I think will be the most useful and interesting based off of that. So if that's false, let me know, and I'll pivot and do something else. Last lecture did have a few suggestions. We pivoted a few times and showed some things that the class wanted. If you just want to see what I want to show and what I think will be interesting, then it's whatever. It's whatever for me because I think it's all interesting. So, so first, before we get started, so we want to talk about O of whatever, O of n. I'm going to start with an O of n versus O of n squared versus O of n log n comparison. But we always talk about these O of, I shouldn't say always, I haven't talked about it too much. But we talk about these O of comparisons and say, oh, this is slow because it's O of n squared. What I want to show is a more practical approach today of what does that really mean? What's the difference between linear, quadratic, I shouldn't use those words, but O of n and O of n squared. Quadratic, O of n squared we usually call quadratic, O of n we call linear. Quadratic confused me for a while, the O of n. I don't know why we call that quadratic. I guess because quadratic doesn't matter. Anyway, so I have this method here, which is going to take a function. This is something we didn't talk about this semester, so don't get tripped up on the syntax. If that syntax is confusing to you, it's not going to be on a quiz. It's not going to be on an interview or anything. I just wanted to show it because it's something we used to cover in the class, but don't anymore. So if you're here for these lectures, I assume you want to see some cool stuff and just new stuff. So it's going to take a function that doesn't take any parameters and returns unit. It's going to mark the start time of that function call the function, and then mark the time where we ended. Get the current time when it ends, subtract that from the start time. That gives us the time that it took to run this function. And then I'm going to print that to the screen. It took this many milliseconds to run the function. We're actually going to give this methods, and then Scala will auto-convert our methods into functions for us. So we're going to write methods that have no parameters and return unit. and then that will this will give us the runtime of how long it took to run that function. We want to write this with different runtimes. So let's first I want to create a list. I just want to create a list and put a bunch of elements in it. I'm going to create a list of random doubles, just random garbage, and do some runtime analysis with it. So let's do list example. It's going to take no parameters and return unit. And I'm going to create a list. I'm going to call it my list. If you're wondering why, like, you see this my list all the time, I use it in a lot of my lecture examples. A lot of times when I'm coding, just legit coding too, a lot of tutorials, they'll usually have like my list or my array or my int or something. The reason we do this is because we know it's not going to conflict with any names in the language we're using or any libraries that we're using. If I just use list, I'll get away with it in Scala, that's fine, but in a lot of languages, list is a word that's used for a variety of things. And like, for example, if I use list with a capital L, I'm going to get in trouble with this. Actually, does Scala let me do that? Because that's the name of a class. It's going to get very confusing when I try to refer to that variable because it's the same as the name of a class. If I name something my list, I'm not going to have that issue because who the hell's writing a library and naming their stuff my list? That's my list. I control that. They shouldn't be doing that. When you write libraries that other people are going to use, don't name something my list or something like that. I'm going to avoid those name conflicts completely. I'm going to create an empty list. And whenever we do runtime, we have some measure of n that we're going to measure the runtime compared to. For data structures, n is the number of elements in that data structure. So let's create a data structure with 1,000 elements to start with. And what I want to do is just say for 0 until n, my list. And I'm going to start with prepend, my list prepend math.random. I did it again. Did that same thing in the last lecture. This has got to be a var if I want to reassign it. And I'm just going to prepend 1,000 elements and create this list. In my main method, I want to call time function and give it list example. Now, if I give it this is going to be an error because I'm calling list example, which returns unit, and then giving time function unit, which isn't what it takes. It takes a function which takes no parameters and returns unit. For the difference, I got to delete these parentheses. At this point, I'm not calling list example in this line in the main method. I'm passing the entire method into another method. That method is converting it in, or Scala actually, is converting this into a function, and then it's calling the function inside that other method. So I'm passing the entire thing, this whole thing, that's what I'm passing. I'm not calling it, I'm just passing the entire thing. And let's run this and see how many milliseconds it takes to run. It takes 123 milliseconds. I want to test something because something I saw in the other lecture. I want to give this a fixed constant and just see what change this gets. I got to satisfy my own curiosity for a second. It is the same amount of time. All right. Okay, so about 100 milliseconds-ish to create a list with 1,000 elements and prepend each of those elements in to that list. If we jump this up to 10,000, so 0.1 seconds, 1,000 milliseconds is a second, so we got 0.1 seconds. With 10,000 elements, still 0.1 seconds. What I want to check with my curiosity, I want to know where that overhead's coming from. So we multiplied our n by 10. We have 10 times the amount of list here, but it's still taking 100 milliseconds. So somewhere in here we have 100 milliseconds of overhead inside this method call. I don't really know where that's coming from. 100,000. 100 milliseconds-ish. We have a little bit of variance. But we have 100 milliseconds of overhead here. Let's go up to 1 million. In 200 milliseconds, we start to see a little bit of increase. Actually, creating the list is becoming a little bit of a burden at 1 million. And I'm pretty sure we can't go up to 10 million. I'll try it just while I'm giving an explanation here. I believe this is the limit where we hit a heap space issue, because the JVM just wasn't giving us enough heap space. Oh, no, never mind. Second and a half. Maybe it must have been 100,000 then. So this is with prepend. So we know that prepend is an O of 1 operation. To prepend to a linked list, you create a new linked list node and have it refer to the head of the list. And you effectively prepend it to that list. This works even with an immutable list, because you create, with the first element, we create a linked list node referring to null. And then we create another node and just have it refer to that node, create another node, have it refer to that node, and just keep doing that 1 million, 10 million times until we have our entire linked list. Every time we prepend another element, we don't have to modify anything with the existing list. So if we have an O of 1 operation and we perform it n times, we have a loop that's going to iterate, that's going to execute n times. This code executes n times. So we have an O of 1 operation that executes n times. We have an O of n operation to construct the entire list, which is as fast as we can possibly create a list of n elements. We have to do at least some work for every single element. And we're doing quite a bit of work. We're allocating memory on the heap. We're asking the JVM for heap space, creating a linked list node, pointing the reference over there. Allocating the memory is the big part of that. And prepending this whole thing. So let's bump this down to where we just saw only the overhead at 100,000. This is the last time where we just saw that 100 millisecond overhead. Change one little symbol. Of course, early in the semester, first learning this Scala, this is going to be, I don't know, what's the difference there? It's not going to really have meaning to you. But now we know that this is append instead of prepend. So with append, this is an O of n operation, because even if this were not an immutable linked list, you would still have to navigate down the entire linked list, find the end of the linked list, and then append the element to the end by having that last element refer to the new node, and then the new node refers to null. So we have to navigate this entire linked list. With Scala's built-in list, we have the extra inefficiency of having to copy the entire list. So each time we append an element, we got to navigate this whole linked list. We're jumping all over memory, .next, 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 finding the element with null, copying the entire linked list, and with that new element appended, it's going to take significantly longer, about half a minute. Just switching from prepend, which we only felt that 0.1 second overhead that we saw even creating a list of 1,000 elements, which is basically free, given whatever that overhead is always there. So the 10,000, 100,000 elements was pretty much free, to half a second. This is something where just being inefficient with the algorithms you use, choosing the wrong algorithm for the data structure that you have, even at 100,000, you could see half a minute of slowdown. If this is something you're calling fairly regularly, you call this 10 times, you're waiting 5 minutes for those method calls to return when they should be taking 0.1 second each to create this list of 100,000 elements. Some of you noticed this in homework 1. You're iterating over the cities.csv, which is over 100,000 lines. We were in this range of 100,000 in homework 1. And if you were creating a list and storing information for every city in that list and appending to the end of the list, you would feel this slowdown. You would run your tests. It would take several minutes because you're calling multiple tests. You'd time out in Autolab and you'd be wondering what's going on. Then I'd be like, prepend instead of append. But more accurately, my answer to that is, don't create a data structure storing all of this data, because you don't need to do that. A lot of students want to store all of that data in the data structure. The answer to that one, when we were doing homework 1, was just process each line as you read it. Read a line, do everything you need with that line, and then just throw it away. You already processed it. You don't need to store anything about that city anymore. But if you were, and you were appending, you hit this really terrible scenario where you have an O of n algorithm, because append is O of n squared. Where append is O of n, this loop is executing n times. So you have an O of n operation executing O of n times. You have an n squared algorithm. So n squared is where we're really starting to limit what we can do with our code. So 100,000, it's a pretty big number, but it gets prohibitively slow if we have n squared algorithms, O of n squared. But with O of n, even when we get up to 1,000,000, 1,000,000 is a pretty small number to a computer, and as long as we're smart with the algorithms we choose and the data structures we work with, we should be able to work with 1,000,000 elements no problem. 1,000,000 elements shouldn't be a big deal to us. So linear runtime, 1,000,000 elements, including allocating space, quarter of a second. Which, depending on your application, can be noteworthy. You might want to get that down a little bit. But in a lot of applications, quarter of a second, we're fine with that. 1,000,000 is a small number to a computer. We usually talk in terms of billions. We talk about gigabytes. We talk about gigahertz. Those are both in the order of billions. 1,000,000, it's not that big of a deal. This program with 1,000,000 doubles, a double is 64 bits, that's 8 bytes. This is going to take 8 megabytes of RAM. If you have a process that's taking 8 megabytes of RAM, you probably don't even care. We got Chrome, which is taking gigabytes of RAM. We're going to be okay with this one. So that's linear versus n squared, and of course going over, if I try to run append on 1,000,000, it might take the rest of lecture to run that thing. It's going to take a long time. So I'm not going to run that one. But half a minute at 100,000 versus quarter of a second at 1,000,000, that's the difference between append and prepend. That's the difference between n squared and n. So a huge difference between those two. N squared, we want to run away from those real quick. But what about sorting? List of double equals list dot sorted. So what about sorting? So we have about a quarter of a second here, and then I'm going to add sorting to it. So whatever number we get here, we want to subtract a quarter of a second-ish, like 200 milliseconds, 250, somewhere in that range. Sorting we can do in n log n. You better believe any implementation in a language is going to be n log n. It's going to be asymptotically optimal. So this is going to be an n log n operation to sort 1,000,000 doubles. So when we add that extra log n factor, how much is that slowdown going to be? Well, we got exactly 1 second. All right, not much. So we went from a quarter of a second to a full second. So it took about 750 milliseconds, 3/4 of a second to sort these things. We got a ×3 factor increase. Now, granted, that linear, we had memory allocation, which really slowed it down quite a bit. But we don't have too much of a slowdown here. ×3 with whatever the constants are. We don't care about constants in asymptotics. And the log n factor. That log n factor is practically a constant, like most of the time. We have a ×3 increase instead of an absolutely absurd increase when we went from n to n squared. But n log n, kind of linear-ish. Like, it's not completely linear, but if you're running smoothly, if your program's running smooth with linear operations, it's probably going to run decently smooth with n log n operations. That log n really didn't add much to the runtime here. Didn't get much runtime increase. Now, again, depending on your application, if you're loading a website and somebody's got to wait a full second for your page to load, well, that's going to get a little prohibitive. If you're serving up 1,000,000 elements to your users and sorting them before loading them up, well, now the difference between a quarter second and a full second, the user's going to feel that. Even a quarter second is kind of slow in that regard. Of course, you're not allocating 1,000,000 elements in a data structure and then shipping them every time a page loads. If you are, you've got to rewrite something there. But n log n, not that big of a deal. That log n factor, it's not that big of a deal. But that line between n log n and n squared is usually the difference between usable and not usable when our numbers get pretty big. If your numbers are like n equals 10, who cares? Use n cubed algorithms for all we care. But once your numbers get decently large, n squared, we couldn't run on 100,000. N log n, we run on 1,000,000 pretty smooth. And just for the sake of argument, with 100,000 running linear and n log n, just our n squared took half a minute. Here we get 0.2 seconds. Huge difference between n squared and n log n. Any questions on this part? Next, I'm going to set up some binary search. Okay, I'm going to change this code a bit. If you have questions, shout them out. I got a little bit of just logistics to get this set up for binary search. And we got to write binary search. I want this to return a list of doubles. So I'm going to reuse this code to return my list of doubles that are already sorted. For binary search to work, the elements have to be sorted, and we also need an array. Binary search only works with a data structure with random access. So we needed this data in an array, and we need it to be sorted. Without being sorted, binary search just doesn't work. So let's call list example and get our sorted list. I did this again. I want this as an array. The list example, I want to actually call it this time and convert it to an array. So now I have a sorted array of random doubles. Oh, I forgot something I want to make sure I mention. I'm going to add one call here. First, let's run this just to get our baseline back. Which was about a quarter of a second. So I'm creating a list of 1,000,000 elements using prepend, about a quarter of a second. And I want to add one line of code. I'm just going to print my list. All I'm going to add, just printing my list out. Should be an O of n operation. But as it turns out, printing to the screen is actually really slow. So just printing to the screen happened to cost us as much of a penalty as sorting. Printing to the screen is actually a very slow, very what we call expensive operation. It takes a lot of time. It takes a lot of processor power. Just printing to the screen. And we can see we got all these random doubles from 0 to 1. In fact, just to show that this is what we're working with, let's get a visual on here. We can see that we are actually sorting these elements. Sorting 1,000,000 elements. I'm not going to scroll through them all because it'll take all day. No, it won't take all day because most of them, the console here only stores so many values and then it starts deleting old values. So we only get up to 0.947 on there. If you ever don't see what's printed to the console, it might be because you printed just too much stuff. So printing to the screen, actually pretty expensive. This can happen in your homework. It's possible. These are really crazy bugs. It's weird to see every time, but it's possible to have a print line actually causing a bug. You can have a situation where you have a print line in there and everything breaks, and you remove the print line, or vice versa, add a print line, and then it works. Or did I say works both times? It works one way and breaks the other way. It's very possible. It does happen. It can happen. I've had those types of bugs before. It's really strange every time. This usually happens when you have concurrent code, where you have a race condition in your code, so that is the actual bug. And then the print line itself slows down one of the pieces of code that's concurrently running to allow the other one to always finish first. And then that can either introduce the bug or expose the bug or hide the bug, either way. And in Autolab, in this course, in academia, if you got print statements like inside a loop here, especially, so if this print statement right here, now printing should be O of n, and it's printing every time you're prepending. So you're going to print a list of size 1, then a list of size 2, list of size 3. It's going to end up all the way up to 1,000,000. It's going to end up being O of n squared at that point. It's going to take forever. It's going to lag my computer. It's going to take a long time, prohibitively long. So in the context of academia, you might have a print line right here, submit to Autolab and get a timeout error. You remove just the print line and you say it shouldn't affect my code at all. You submit again and everything's fine. You get full credit. This can happen, especially like 250 where they're measuring your runtime as part of your grade. Make sure you don't leave those print lines in because that's going to hurt you. That's going to hit your runtime pretty hard. In something like this, or with the cities example, storing all the cities in a data structure, but you're prepending so it's efficient, but you're printing out the list every iteration, but you're testing on a smaller file than what I'm testing with in Autolab, so you don't see the bug on your end. Like things like that can happen, and you end up getting hit by a print statement. I'm not going to wait for this to finish because it's going to take all day and burn up my laptop. But one print statement, one print line right there is the difference between my fan starting to spin up, my CPU starting to melt and everything. One print line is the difference between that and just running fine in 1 second. So be careful with those print lines. It's a deceivingly expensive operation. So we're sorting these things. Comment this out. I have a sorted array, and I want to write binary search. So first, since we want something to compare it with, let's do linear search. And actually, I want to, before we get there, like to, so I have an issue. Like, we're not going to get arrays large enough to see the full difference here is the problem. I want to try to fix that real quick, but I don't know if I'll do it fast enough. So my array of double and some value that we want to find in this array is a double. To find. And we're just going to return unit because we're not actually running this stuff. And I'll just print to the screen for the values that we find. So I want to find a value in this array. This is the standard way to do it. This is the way you would do it if you had this as a 115 assignment. You would say for I in my array dot indices. If my array of I, and this is doubles, so normally you would say equal to find. This is doubles, so of course we're not going to do that. But if math.abs of the difference is less than epsilon, I have to define val epsilon double equals, and I can go pretty low. You can see how much precision we have, so I can go pretty low on my value here. Got it. And I want to print out what value I found. So I found this value, just to verify that we actually did find the right value, at index I. And I'm going to do something I said never to do in Scala, that we don't like to do it, but just for the sake of making this a little easier to write, I'm going to put a return right here. And then if we found the thing, I'm going to say just print that we found it and return. If we get to the end of this loop, that means we went through the entire array without finding the value, and at that point I can say print line never found the thing. This is our linear search. We're just going through every single element in the array, checking if it's close enough to the one that we're looking for. And if it is, we got it. If we get through the whole thing without finding it, we never got there. Okay, so that's linear search. Now let's get binary search in here. Binary search. And for this, I want a few, well, let me just do it naturally. So for this, I want to find the midpoint of the array, check that value if it's the value I'm looking for. If it's not, check if the value I'm looking for is higher or lower, and then split the array in half with the remaining elements that I want to find. Actually, I am just going to go for the whole thing. So instead of actually chopping up the array every time I narrow down the search space, I'm going to use some inputs for lower bound, and that's the index of the lower bound of my search space, my remaining search space, which will start at 0, and then my upper bound, which is going to be which is the upper bound of my search space. And that's going to tell me what's left in the array for me to look through. So initially it's the entire array, 0 and length minus 1. And then if the midpoint is less than what I'm looking for, which way am I going? Less than what I'm looking for, then I'm going to move this up to the midpoint, the lower bound up to the midpoint. And then if the midpoint is less than what I'm looking for, I'm moving the upper bound to the midpoint and then slowly narrowing down my search space in this array. So I don't have to mess with the data structure at all. This array can be immutable. I don't care. I'm not going to mess with it at all. I'm just going to look at different sections of it at a time. But this isn't how I want to call the method. If I gave you a search method or some library has a search method and it's like, please specify the lower and upper bound. Like then you got to read documentation, figure out what they mean by upper and lower bound. It's kind of a pain. So when we actually write this method, we want another method. This is the public-facing interface that people are actually going to call, and we're just going to return unit still because we're not going to use this stuff. And then this is just going to call binary search helper, forward the inputs, and start at 0, myArray.length minus 1. So we're going to set our initial bounds, and then this method is going to actually do the thing, which probably should have opened with this, but I'm setting up recursion for this. With recursion, we usually have these helper methods, and the helper method is actually doing the recursion, and we have an extra method, which is going to be the public interface, the one that people are actually going to call. So we have the upper and lower bounds. I want to find the midpoint, which is going to be the lower bound plus the upper bound over 2. And I want integer division here because I want the result to be a whole number. I want it to be an int. So even if the sum of these is an odd number, I'm just going to take the floor of that and get something close to the midpoint. Either the midpoint or the midpoint isn't a whole number, so I'm going to take the floor of it. So I got the midpoint. I have the value. I can get the value that I'm currently considering. is a double, which is going to be my array of mid. And now I want to check my base case. I want to check, is this the thing that I'm looking for? I'm going to reuse some code here. I'm going to say if value to check is within epsilon of what I'm looking for, we got it. Place my variables here. Mid. We got it. That's this whole part. I'm going to get rid of this because I don't need it anymore. Else if value to check is less than to find. So if the value I'm checking, that's the value at the midpoint, if that's less than what I'm trying to find, I want to move the lower bound up to the midpoint. So I'm going to make a recursive call, binary search helper, my array, that doesn't change. What we're looking for doesn't change. But the lower bound is now going to be mid, because what I'm looking for is higher than the midpoint, so I must be searching in the upper half of the array. And the upper bound is still the same. Else, what I'm looking for must be greater than to find. And I'm going to do just the opposite. The lower bound stays the same, and the upper bound moves to the mid. And I have one issue with this code. Where do I put this highlighted thing? And what is the issue overall? There's a big, big problem with the way I have this written right now. Yes. Right. Yeah, so it's never going to hit that print statement. So what can we change here to get it to hit that print statement? Like how do we know if we didn't find the thing we're looking for? So the issue right here is that we have one base case, only one case. We have 3 different cases. 2 of them make recursive calls, and we only have one base case that doesn't make a recursive call. And that's when we found the thing we're looking for. We found something within epsilon. But if the element we're looking for, if toFind is not in this array, we're never going to hit this case. And we're going to have infinite recursion. We're just going to keep making recursive calls forever and get a stack, actually not a Stack Overflow, but we're going to get infinite recursion here. So what we want is another base case that checks if we didn't find the thing that we're looking for, and that's when there's no search space left, which is when upper bound minus lower bound less than or equal to 1. I had in the last class, I know this because I just made this mistake in the last lecture. I said if upper bound equals lower bound, then we have no search space left. It's just one value, and we just checked that value right here. And I had infinite recursion. So if the difference is only 1, then is 1 or less, then we know we haven't found the thing. Because the only way to have a recursive call where, I guess this isn't 100% true, but to get a recursive call with a specific lower and upper bound, that upper and lower bounds, the values at those indices, had to have already been checked. It's not 100% because we never checked 0 and length minus 1. We might be missing the endpoints in this implementation. So I might have a bug that would be a perfect bug for a unit test. That would be one of my edge cases I would test for, and then this code might break on that, depending on how everything absolutely rolls out. I think the lower bound would be checked because of this floor, but I don't think my upper bound is ever checked. So if you, that's something that I'd have test cases for, I'd have incorrect solutions. If I gave this as a problem on a homework, I'd have incorrect solutions for that. And to fix that, you would just check the endpoints right here would probably be the easiest way, or finagle it down here somewhere to make sure those are checked. But I'm going to say if upper bound and lower bound have a difference of 1 or less, we didn't find the thing. That's our binary search. Quite a bit more code than linear search. Let's bump this down to 100,000 to start off at a low example. But quite a bit more code in my annotation. So this is tail recursive. That's why I bit my tongue. It won't have a stack overflow because this is tail recursive the way that I wrote it. So it will reuse these stack frames for these recursive calls since it's the last thing that the method does. But it would go infinite. When I said upper bound equals lower bound here, it does go infinite. It just doesn't cause a stack overflow. But that's much simpler than this. This code is a lot simpler. And this can be deceiving at first. Just because you have a lot more code doesn't mean you're a lot slower. In fact, we of course know by now binary search is extremely faster, much, much faster than linear search. Because of runtime analysis. We know that. So let's time these things. We have our sorted array. We're going to time, and we're going to add some print statements here. Running linear search. Linear search. And my methods don't take no parameters. My timing has to take no parameters here. So I have to do a little trickery here. If you want to know about this, you can ask in chat. I'll be happy to explain it. But I might as well just explain it. I'm just creating a function that calls my method. So I'm going to call this with sorted array. This function doesn't take any parameters and just calls my thing that does take parameters. And let's find 0.2384. And let's find this thing. So we're going to run that. We're going to duplicate this, run binary search. The name of the thing. And this is where I get the benefit. When I call this thing, I just want to call, in this array, find this thing. I don't want to have to say, wait, you want upper and lower bound as arguments as well? I don't want to mess with any of that. So this just calls the helper method, which sets the initial values for lower and upper bound to what they're supposed to be. When I'm looking for a value in an array, I want to think about as little as possible. I just want to think about the problem at hand, whatever I'm coding. Run these things. So we know linear search is going to be O of n operations. The very worst case is you don't find the value in the array. So you have to, actually I might as well give the worst case. Linear search never found the thing. Oh no. Neither of them never found the thing. My epsilon might be a little too low. We are dealing with randomness, so I have to randomly get a value within epsilon of that. It might just not happen. Because there's... Not sharing an epsilon. I'd believe that maybe my binary search, I might have messed something up there. There's no way I messed up linear search, though. Okay. What was my value? 2384. So we did just barely get in there. And they both found the same value at the same index. So yeah, I think my epsilon was just a little too stringent there. So linear search, 17 milliseconds. We're not allocating, so this is O of n, just like prepending and creating the list to begin with, but we're not allocating memory. We're not doing anything very expensive. we're just looking up elements in an array with random access, which is O of 1. That's why we can't do binary search with a linked list. We'd have to navigate the whole linked list just to find the midpoint. We have to go .next, n over 2 times just to get to the midpoint, which throws away all of our gains already. It'd be useless. This is a useless algorithm for linked lists. But with an array, we're just looking up an index, finding the value at the mid, and then cutting our search space in half every time for binary search. Sorry, I was explaining linear search. Linear search is linear, but we're not allocating anything. We're just, what's the value at this memory address? What's the value at this memory address? Just lookups, not allocation. Much, much faster. Binary search, we're just looking at the midpoint, cutting our search space in half, looking at the midpoint, cutting our search space in half, and continuously doing that, dividing our search space by 2 every single time we check one value. So 17 versus 0. Let's bump up our n to 1,000,000. And again, we're not allocating anything, so we're not even going to feel much pain on linear search. We're feeling pain, a little bit of pain right now just because we're creating the list and sorting it. But when it comes to finding an element, even that O of n, much smaller constants without memory allocation, 28 milliseconds to find a value linearly. I shouldn't have picked something so early in the thing. Let's change this to a 9, just so linear search gets a little more penalty. And we found 2 different values. So we had multiple values within epsilon of this value at that point. Just randomness gave us that. So we're feeling pain just from creating the list, sorting it, and then converting it to an array. All that's kind of expensive at these numbers. But then finding things, even linear search going almost to the end of the array, not that much time taken. When we have even sometimes inefficient algorithms aren't that bad. If you're doing this 1,000 times in your program, it's going to start piling up. 35 milliseconds is pretty slow for something like this, but not prohibitively so. You can get away with something like linear search quite a bit, as long as you're not like appending to a linked list. If you're not doing something like that, if you're not adding elements to an array, it would be pretty slow as well, and reallocating everything. Was it 10,000 that gives me the error? Or 10 million? No, I'm at 100 million right now. 100 million gives me a heap space error. This one's not going to run. I'm not going to wait for that to happen. But 10 million we get to see. It is 10 million, right? Yeah, 10 million. We get to see that we're starting to see a little bit of runtime in linear search, but that binary search is still at 0. Like, it's taking almost no time at all. Because with linear search, you got to go through all O of 1 things. And when we saw O of n was kind of slow already, but when we went from O of n to O of n log n, there wasn't too much of a difference. It was a factor of 3. It wasn't too big of a difference. That log n didn't make too much of a difference. So when we take away the n completely and just have log n, that's almost a free algorithm. It's like almost O of 1. It's very efficient, very fast. The difference between O of 1 and log n isn't that much. The difference between O of n and O of n log n, not that much. Those log n terms just don't hurt us all that much. But the difference between O of n and log n, that's a huge jump. The difference between O of n log n and O of n squared, that's a big jump. Those are the jumps that we got to be concerned about. So this is almost free. Even if we had an array of 1 billion elements, I think I started saying this right. Even if I have an array of 1 billion elements, linear search has to search through 1 billion elements, right? Of course, it's linear. It's got to search through 1 billion. Log n binary search, how many checks does it have to make? We're almost out of time, so I'll just give the answer. 30. 30 checks versus 1 billion. That's how powerful log n is. That's how slow log n grows. You know that from math class. But now we can take advantage of that slow growth. If we have a log n algorithm, it's basically free to run it. I'm actually out of time. So with that, have a great weekend. I'll see you all on Monday.